Entropy balance and generation would be the topic of this lecture. In the early part of the class, we analyzed Carnot engines. Carnot cycle both ways as an engine or as a refrigerator, and derived bounds for efficiency. What's the maximum work that can be delivered via a Carnot engine? Or if you have a refrigerator or heat pump, say, what is the minimum work that has to be incorporated in the system? Then we moved on to looking at flow devices. We wanted to get efficiency bounds for such systems. So in the previous lecture, we derived one such bound. We said the maximum efficiency is obtained in an ideal reversible device. What is the connection between the actual device and the real device, ideal device and the real device? The initial condition Pt is the same. The exit pressure is the same between both of them. However, in the ideal device, it is an isoentropic operation. Okay, so the entropy of the inlet and outlet is one and the same, and there is internal reversibility. So this, for example, if you're thinking about a turbine, so this gave us a bound, okay, on what can be the maximum work that can be obtained. Supposing if you neglect kinetic and potential energy changes, you can equate the work to enthalpy changes, and we can derive such a bound. Likewise, if you are, let's say, operating a compressor or a pump using an isoentropic operation, you can get a bound on the work that is required. Okay, so what is the minimal amount of work that needs to be incorporated into the system, either in a compressor or in a pump? But what is the actual compressor work in this case, or the pump work in this case? All right. So this gave us a measure of efficiency. That's what we looked at in the previous lecture. Now we move on to a related topic involving entropy balance. Okay, so in all these cases, we would see in the next lecture or the next series of lectures how entropy generation and irreversibilities are connected with so-called lost work in the system. We'll look at that. So the context for the next few lectures is provided by this and the last few lectures. So first, let's contrast a balance which you have known from your high school. Okay, mass and energy balance. Okay, so mass and energy can be transferred across boundaries. Mass and energy are conserved quantities. Okay, so we're not going to relativistic limit or E is equal to mc squared into conversion of mass and energy, but within simple engineering scientific context, a mass is separately conserved, energy is separately conserved, and we can write a balance equation because energy and mass are neither created or destroyed. However, we are looking at entropy. We say entropy can be transferred, so we must be clear what is getting transferred. Let's say, is it heat that is getting transferred, or is it entropy that is getting transferred? If it is heat transfer, is rather obvious. But if you say entropy transfer, so we need to think through that more carefully. We emphasized quite a lot that entropy is not a conserved quantity, okay, and it is generated in an irreversible processes. And what is challenging is all the real processes, okay, that you see are actually irreversible processes. Okay, so how do we deal with such a scenario? All these things in a way boils down to Clausius inequality. So we analyzed that in a few earlier lectures, and we use Clausius inequality to demarcate what is a reversible process and what is an irreversible process. It boils down to this question. Can we write a balance equation for something that is not conserved? So that's the question we're going to address in this lecture. In my opinion, many things about entropy, when you look at it from classical thermodynamics, macroscopic thermodynamics, it is very mysterious. Okay, so I find a lot more understanding if we can look at entropy from microscopic so that you get a good physical picture of what is happening. We did this in some earlier lecture. So I request you to go back and get a concrete understanding of how we looked at entropy microscopically. So we did one important pedagogical example of a Joule expansion, right? So this is what is called Joule expansion. There's a free expansion. We addressed this using classical thermodynamics and derived an entropy change expression. And we devised a simple model to calculate entropy change from microscopic. We see here we are not really appealing to any molecular properties. We are treating everything as a continuum. But here we are assigning some volume to the atoms, and then we are saying that the atoms are distributed in a particular way. We interpreted entropy in the following manner. Supposing there is a macroscopic system wherein you control the total internal energy, volume, and the number of molecules. So this entire system can be attained in a certain number of ways. We call that the degeneracy of a system. This is what is called the degeneracy of the system. So entropy is a measure of the degeneracy of a system. Okay, so supposing this is an isolated system, you can control U, V, N. There is no exchange of work or heat between this system and the surrounding. There's no exchange of mass and so on. So if you supposing you create a system that's not at equilibrium, the system will decay towards entropy maximum. At equilibrium, entropy won't change, but as it goes towards equilibrium, entropy will go towards the maximum. Okay, so that is, given a macroscopic condition, the system tries to distribute itself in as many ways as it can, okay, given the constraint. And what do we mean by the constraint? These are the constraints. So isolated system looks artificial because maybe we don't typically control these things. So this was a formula that was derived by Boltzmann. Gibbs extended such an analysis to a system wherein you control T, okay, temperature. It's important to understand when you control temperature, U is not being controlled. U can fluctuate, okay. So this is some point that people find it hard to understand. Okay, so the average, see, T is a measure of average U, okay, in each degree of freedom. But when you control fixed T, the total internal energy can fluctuate. Okay, so again, this can be interpreted, this is called the partition function, can be interpreted as average degeneracy of a system. Okay, so given a macroscopic state, there are numerous microscopic states that are equivalent in the sense that for all those microscopic states, in temperature, volume, and total number of molecules is the same. And entropy is interpreted via this degeneracy. So here we are interpreting entropy via this degeneracy. All right, so there is a version of thermodynamics or postulatory thermodynamics or axiomatic thermodynamics. We say that corresponding to the control macroscopic variables, some particular thermodynamic function takes an extremal value. So supposing you control U, V, and N, entropy takes an extremal value. It takes a maximum. Supposing you control T, V, and N, free energy, in this case Helmholtz free energy, takes an extremal value, in this case a minimum, and so on. If you have questions on this, let's discuss this further during the discussion session, because it's very, very important. This gives you a better physical picture of what's going on. Okay, so let's get back to entropy balance. So our objective was to write a balance equation. So this is a way of writing a balance equation facilitated by this term called entropy generation. Okay. So how are we writing this balance equation? There is some entropy that is entering into the system, there is entropy leaving into the system, and then there is change in entropy of the total system. When you try to account for this via these two, they're not one and the same. There is an additional term that develops, that is called the entropy generation term. Okay, so you have to contrast this with energy or mass conservation. Okay, in energy and mass conservation, these two exist, this term exists, but this doesn't exist. It's always zero. Right, so that is important to know. So contrast, this is something which you have known, energy conservation, but the new topic concept which you are trying to get familiarized, it has to do with entropy generation term. So there can be entropy getting in, because entropy is a state quantity, it can get in either by mass flow inside the system or heat flow into the system. Entropy can get out, again by mass flow or by heat flow. But when you write a balance equation, there is an additional term that needs to be incorporated. That's called entropy generation or entropy production. This will become more clear when you do some examples. Okay, so this I encourage you to look at all the solved examples in the textbook, because this is a slightly confusing topic to many students. So it's important to first think through what we mean by entropy generation, why that is so, and then look at some examples to become clear about this. So for example, we can look at entropy transfer via heat. So in this, let's say you have a surrounding, heat gets transferred from the surrounding to the system. So we are only looking at, let's say, the entropy transfer, entropy changes in the system, for example. So what is important is you assign temperature for the boundary, and let's say 500 kilojoules is being transferred from the surrounding to the system. So the entropy increase of the system via transfer of heat is this divided by the temperature of the system, right? So that is, in this case, 1.25 kilojoules per Kelvin. So here it's important to assign the temperature at the boundary. So we can also have a system wherein different parts of the system are at different temperatures. You will see in fairly complex engineering systems, this is also a possibility. And entropy transfer occurs from different boundaries. Okay, that is also a possibility. We can look at you can look at such examples in your text. We do not say that entropy is transferred by work. Okay, so whenever we think about entropy, we are thinking about heat. Okay, so at a molecular level, at a microscopic level, heat is, we talked about this, what we mean by heat. Okay, so we are always thinking about kinetic energy or distributed in various degrees of freedom, okay, molecular degrees of freedom, equipartition into various degrees of freedom. Whereas work, we said that work involves raising and lowering of mass. Okay, so supposing, so here we are thinking about shaft work. So you can raise the mass by rotating a shaft in a particular manner, or lower the mass by rotating the shaft in the opposite manner. Okay. However, when we think about heat, you cannot, all this heat cannot make all the, when we say heat, it's the thermal energy stored in the molecular degrees of freedom. All this heat cannot come together to rotate the shaft in a particular way, okay, in a particular direction. Okay? So while all of work can be converted to heat, the other way around is not possible. So by definition, we don't assign any entropy transfer to work, and there are irreversibilities. That is, this work, shaft work, is converted to heat. Okay, what do we mean by irreversibility? This statement I made, that all of work can be converted to heat, but heat, the opposite, the heat being converted to work, is not possible. Okay, so that's where the irreversibility comes in. All right. So this, when you do some shaft work, the shaft generates heat, and that can generate entropy. Okay, but we don't really say work transfer results in entropy changes. There can also be entropy transfer by mass flow, because entropy is a state property. Supposing you have a control volume and there is a certain amount of mass that is input into the system, and that comes in with a particular intensive quantity, the enthalpy and entropy as stated here, you can calculate the amount of entropy transfer via mass flow by knowing the velocity at this point, cross section, density, that will give you the mass, times the intensive quantity, that's in a specific entropy. Okay, so that will give you the net rate of entropy that is coming in due to certain mass flow rate. And you can further integrate it over a particular time differential to get the overall entropy transferred via mass flow. Let's write out the balance equation for first, the simplest case, a closed system. So in a closed system, you have a system, and at a sufficiently far away boundary, you can assign a constant temperature. So there might be temperature variations here due to heat transfer. However, there at a sufficiently, you can always find out a sufficiently large boundary where you can assign a particular temperature to the surrounding. For a closed system, let's, this is, first we look at the entropy change for a system, right? So we will do example in the next slide, where this becomes, I think there will be an additional clarity on how you implement this and why the numbers turn out to be what they are. So there can be heat transfer, heat interaction between the system and the environment. And we are talking about this. Tk refers to temperature at the boundary of the system. In this case, it can also be different. Supposing for a more complex system, the system can interact with the surrounding at different temperatures. Right? So when you So let's clarify this in the next slide. Okay, it will become more clear. So for a closed system, what we are trying to say, there is entropy change of the system. There is an entropy change because of heat interaction with the surrounding, and to account for the differences, you have this entropy generation term. So how do we talk about entropy of the system? You say the entropy at the final state minus the entropy of the initial state times the mass. So, and then you have entropy of the surrounding, which is corresponding to this term, that is Q surrounding divided by T surrounding. No, so I mean, I don't know whether I stated it clearly. So it will become more clear in the next slide what this temperature is about. For example, let's consider this particular example. You have a two-phase system, water and water vapor at 100 degrees centigrade. And water is condensing. So because of the new bonds that are formed, internal energy is being released as heat. You're keeping the temperature constant, let's say. And then because of condensation, 600 kilojoules of energy, thermal energy, is being released. And the temperature of surrounding is 25 degrees centigrade. So there are two computations you have to make. First is Q divided by temperature of the system. Okay, so that is minus 600 because energy, thermal energy is being released, heat is being transferred out of the system, divided by the temperature. This is a negative quantity because heat is being transferred. So if you see that, that corresponds to this expression. Okay, so the delta S of a system in this case, in this particular example, is this quantity. Then we have that heat is transferred to surrounding at 25 degrees centigrade. So that is the temperature here. Because heat is gained by the surrounding, there is increase in the entropy of the surrounding. Okay, this term corresponds to this particular quantity. Okay, so this is the surrounding temperature. So that is the temperature here. And then when you add up this is a positive quantity. When you add up this positive quantity with the negative quantity, there is a difference. Okay, so it's not zero. So some new entropy is generated. Okay, this, if you see crucially, the difference between the temperature of the system and the environment, this temperature differential is the prime reason, central reason for entropy generation. Okay, so you have to be very clear what is the reason for entropy generation. It is an irreversible heat transfer. When is the heat transfer irreversible? When there is a finite temperature difference between the system and the surrounding. So that is the reason for entropy generation. So this is a nice example. So let us say there is a system and surrounding, there is heat transfer. And this heat transfer is an irreversible process because heat will always transfer only from region of high temperature to low temperature. So a small change in this temperature cannot reverse heat flow because there's a finite temperature difference between the system and environment, system and surrounding. So this much amount of heat is being transferred. So entropy lost by the system is this quantity. Entropy gained by the system, because entropy gained by the surrounding is this amount of heat divided by the temperature of the surrounding. Because temperature of the surrounding is less than that of the system, the entropy gained by the surrounding is much more than the entropy that is lost by the system, and this difference comes out to be S generation, entropy production. So you can also have a finite wall, and there can be a finite temperature difference. So this is where the entropy is being generated. In this case, there is entropy is in a way generated at this interface. Here, the entropy is generated at the finite wall. Why? In a way, because we are bookkeeping only 2 points. We are bookkeeping entropy lost here and entropy gained here. Any difference, you say you assign it to entropy generation in this region. Likewise, supposing in most of the cases when there is heat transfer, the heat of the temperature of the surrounding doesn't become T surrounding at this point. There is a slightly higher temperature here, and then it reaches asymptotically the temperature of the surrounding. So we assign the entropy generation not only to entropy generation within the wall, but also entropy generation in a region of the air surrounding the wall. Okay, so on either side. Okay, so that's important to understand. So this provides a reasonable, clear picture on why there is entropy generation because of a finite temperature difference. There is an example in your textbook, so you can go over that, which sort of maps this concept into a concrete example. So I urge you to go through the examples, solved examples in the textbook, so to get a better appreciation of the concepts we are discussing in this lecture. Because it's more abstract than the entire topic of entropy itself is abstract. So it's useful to work out some problems to make sure you understand this things clear. Then we can also look at flow device. That's been our philosophy, right? We first look at a closed system, then extend the analysis to a flow device, because in engineering systems, flow devices are very common. So what is different here compared to the previous example? In the previous example, for a closed system, you had this term and this term and this term, but you didn't have this term. So in a flow device, there can be mass flow in and out, which brings in entropy, because entropy is a state quantity, and entropy is taken out by the mass flow rate out of the system. And when you write the balance equation, there is this additional term, which is entropy production, entropy generation. So this entropy can be written either as an extensive form or as an intensive form. In an intensive form, it's per kg. So you can also write it not only in terms of energy, you can also write it in terms of power. Okay, so all these things are going to be very important when you look at power cycles and many of your engineering applications. This form of balance equation is very important. For example, let us look at a simple flow process, which is throttling, which is one of the most simple situation you may have. You just throttle flow via a valve. So you have some pressure at the inlet. Because of the valve, the pressure decreases. How do we characterize this system? We say we do balance, and the enthalpy is said to be a constant, right? So we can analyze these systems. We've already analyzed such systems. So you are in this is a T versus entropy graph. You are in a region where, on a curve where enthalpy is the same. This also tells you the difference in entropy that between the outlet after throttling and before throttling. Okay, so that difference is what shows up as entropy generation term. All right, so go back and first understand these curves. You looked at such curves, and then but the point here is you're in a throttling process. We are in a curve where enthalpy is conserved. that gives you an idea of what is the outlet entropy. And then that helps you compute the entropy generation in this process. So the next major topic we will be covering is Exergy analysis. This has very practical applications. So the second law, which is framed in an abstract manner in the beginning, is added with many practical elements like flow and so on, so that it becomes useful for analysis of engineering systems. So we will start this lecture on Exergy in the next time, and we'll cover it over a series of lectures. Thank you.